Let's get started. Do you guys have any homework questions? On the homework that's due this Sunday. We can talk about the next one too. On the stuff in 11.7. How about on the one that's due this Sunday? Any ambitious people get started on that one yet? I haven't looked to see and I won't pull it up. Well, I will pull up the homework assignment, but not who's actually done it. So this is the one that is due the Sunday after that. So that would be whatever that is, the 16th maybe is the date on there. Sections 12.1, 12.2, and 12.3, which we haven't really gotten super far in yet. So if you do start this, you're probably not going to get super far at this point. You should be able to get the first few questions. Okay, and we're going to pick up. I did go back and graph that question we ended with last time, so we can kind of see what we're doing. We use that to kind of review. So anyway, feel free to work on this when you get time. It is posted. It's due in about a week. Yes.
I do have a question on the homework, number 3.
On the one that's due this Sunday?
Yes, ma'am.
All right, so the one about finding cylindrical coordinates for y equals x squared?
Yeah.
Okay.
I don't understand why. I did it, but it wasn't, they said the answer was wrong.
Okay. Let me put it over here so we can write on it. All right, so how could we do this? We are given the xy equation. We want to go through and find cylindrical coordinates. Which one is cylindrical coordinates? What does that mean we're looking for? In terms of what?
The y, I mean the r.
Yeah, this was going to have theta though. So what I'm going for on that question is like, we're going to go from x, y, and z to r, theta, and z, exactly. Okay. So what could we do on this? How can we do this conversion? Is this like, when we're doing the conversions between those, we want to have like x squared plus y squared equals r squared, but we don't have that. We'd like to have like tangent of, or something of y over x. We don't have that there. There's no real shortcuts we can use for this one. So this is going back and using the fact that y equals r sine theta and x equals r cosine theta. And we're going to go back and just do that substitution. And if nothing else and you can't see any shortcuts, this substitution always works here. So if we go back and do this, we have r sine theta equals r cosine theta squared. And then it's a matter of going through and trying to rewrite this, trying to solve it for r ideally. So we can square both terms on the right-hand side. We can divide through by r. So I'll cancel that one out over there. Now we just have an r over here. Let's go through and divide by cosine at the same time, just so I don't have to write another thing down. So if we clean it up a little bit, sine theta over cosine theta equals r. Let's actually divide by cosine squared, since that's what it says there. Sorry, I should say squared.
So, okay, it has nothing to do with this one, but there's on the case. So
okay. So to finish this problem off, if we stop like this, it's not really wrong, but we know that we can write, when trig functions in our denominator, we have the reciprocals, we can write it as. So this could be written a whole bunch of different ways here, but one way we do it, make a sine over cosine, that is a definition of tangent. And then we're still left with 1 over cosine, which is the secant. So there's one way we can write it, and that's probably the most efficient, probably what a sign would like to see when we write it there. But what's said by that isn't wrong. If you wrote it as sine theta times, that'd be secant squared, that's not wrong either. There's lots of ways you can do it and write this, but that's what I would say. If there's no like shortcuts you can see to get from one to the other, is you can always go back and do this substitution. Okay. So does that help a little, Edwin?
Yes, ma'am. Thank you.
No problem.
I wasn't seeing the substitution.
Okay, yeah, substitution. It's kind of a long way to do these problems, but it does always work. And sometimes it's the only way you can do them. So. Right. We'll get to your test question later, Russell.
yeah,
We can do that after. Okay, that is not the page we were on. We left off on the bottom of page 3.
Hey, what do I go to print that out? I forgot.
Yeah, that's a good question. So the blank notes are on Canvas, but I forgot to send you the completed notes. So you can't go print those off because I didn't do it. But I will send them to you after class today.
Okay.
I'm
How do I
sorry.
get? What do I click on for the blank notes again?
If you go to Canvas, there should be chapter 12. Pull it up here. So, and again, the Garden City Canvas, not your Canvas page.
Right.
But under modules, I have it organized by chapter, and unless I didn't publish it, Yeah, I did publish it. My goodness, that little stupid green button gets me every time. Now you should be able to see them.
Oh,
That
okay.
little green button is checked. So I'm sorry about that.
That's fine.
You can see on the teacher side, even if you have the little green check mark by like the link you want, if the whole entire folder isn't published, you can't see it. And I always forget to publish the folder. So now it's there. You should be able to go see it. And I'll give you the completed notes too. Okay, so let's do a little review here of what we talked about yesterday. So for a vector value function, if I back up to page 1 there, we had our definition of it. Pretty much just a parametric equation. Our parametric function, we're just sticking the 3 parts here to make it a vector here. So we're going to have the x change in terms of t, the y, and the z all talk about this in terms of t here. So a lot of what we do at vector value functions, a lot of what we've done so far, is just reparameterize things that we work with in regular x, y, z coordinates there. So if we keep in mind that we are just taking a regular function in 2 or 3 dimensions and reparameterizing it to be in terms of t, the vector value function basically just sticks together as a vector. And there's benefits of doing that. We'll see as we work with it today and throughout the next few sections here. But we mostly just went through and practiced that so far. So in example 6, not only did we go through and parameterize this, which we have marked right here, but we were looking at that's what we were doing. We were finding the intersection of these curves here. So here is the graph of them. And I could not still figure out how to get this to just graph on the top, so I had to make a new equation. But there is that ellipse that we were working with, that I was able to just get the top half of when we graphed it, because remember one of the restrictions in that example was z had to be greater than 0. I could not figure out a way to do it for the parabola, so I'm sorry. But the parabola would also end at that xy plane where that green thing ends. I just could not figure out how to get it to do that, so I just quit. But then what we were asked to do in that example was say, okay, well, where do these two things intersect? And we can see that they definitely do intersect. There's this path where the ellipse and where the parabolic cylinder definitely cross each other. We went through, we had that equation, and here is the actual curve where those two things intersect there. So you can see it's on the surface of that ellipse, but it's tracing along where that parabolic cylinder is, and that was the equation that we came up with there.
So for ellipses and well, I guess for ellipse, is it hollow?
Yes, so all these are just surfaces, they're all just hollow. We will eventually talk about how to find the volume of them, but when we're talking about these equations are just the hollow outside. So that's all it's talking about. Okay, and then the vector value functions is actually just this. It's not even like a surface, it's just a line that we're drawing through space there. You got the surfaces are hollow. Okay. So that was the thing that we came up with at the end of the hour yesterday. That little red line is what we were working with. And like I said, you can see that it definitely kind of follows along where those two guys are. Okay. All right. So example 7. Example 7 isn't so much, again, math. It's just kind of hopefully understanding what the parts of this we're doing here. So we're given a vector value function, right? This guy right here. I'm going to go back and graph with GeoGebra in just a minute there. But remember what this vector value function tells me. We essentially have 3 little parametric equations that we are tacking together because we have a more efficient way of writing it than as 3 separate equations. So here's the 3 components that we're working with. Okay, we have the one in the I direction or X direction, the Y, and then the Z there. Okay. In the next section, we'll start doing calculus with this stuff here. This whole section is still just kind of setting up and seeing what's going on here. So I'm going to go back, I'm going to graph it, but what we're going to do is say, okay, if we make these changes to these functions here, so what we see in A through E, if we make these changes, how does it affect my function here? And so if you think back to stuff from college algebra when you're doing transformations and things like that, if we have, say, a parabola and we subtract 2 from it, what does that minus 2 do to the function? Shift it down. If we have plus 2, we know we're shifting it up. If we have something where that's inside parentheses, we know that's different. So it's kind of the equivalent of that. Is how do we make these changes to the function by subtracting at different parts here or multiplying by different numbers, and what change is that going to make on my actual surface of the path that I'm working on? So that's kind of the goal of this question. But let me get it graphed, and then we can see what's going on. And if you do use this GeoGebra app for yourself at all, to do a parametric equation, you just do parentheses and then each of your 3 components there. So it's fairly easy. Just type it in there. All right, so we have 2 times cosine t. Oh, and this is a different language. I don't know what I did. I can read some of these things. Oh no. Oh no. I really don't know how to fix this.
In Google Translate.
I could, but
It's in,
You're gonna refresh the page.
go to,
Just close out of it.
I can't handle other languages. Let's go back and use this one. This one is all still in English. Let's just do that. I really wanted to save.
Back in.
Oh, we'll just do this. This was the one I had before. We'll just use the same graph again. It's still in English. Let's see. Okay. Oh yeah, transit this page because you're going to be in a different language too. Oh, what did I do?
it's pretty,
Nope. Okay, I can still do this. It's just math, right? That didn't help me. That translated like to the opposite of what I wanted. What language is this? With all these consonants and J's. Not Spanish, that's for sure.
Russian.
Maybe, I don't know. Okay. Oh man, look at all this. Good thing there's icons. All right, well, let's hope I can still do this. Okay, 2 times cosine of t. 2 times, as long as there's no problems, I should be okay. 1/2 times t. Okay, so we're good so far. Yay, math. Okay. So there is the space curve that we're working with in example 7. Okay, it's again just one of those corkscrews, which if you think about it, hopefully makes sense. If you ignore the z component, cosine of t, sine of t, if you think back to our polar coordinates, that's just talking about a circle here. And we did something similar yesterday. We talked about this as well. So if we look at this thing from the top down, it is just a circle, and we're just basically making this thing into, we're just stretching it out there. Okay, so Wyatt likes to do this on me, but it did it. Okay, let's go through and make these changes. So in A, it says we are going to have cosine of t minus 1. Minus, go. Can you tell what happened to that thing there? If you look at it from the top, we can maybe see a little better.
Wait,
Is that circle still centered at the origin? No, our circle's been shifted here, and it's kind of hard to see the changes. Let me see.
so it goes opposite of what our normal shifts go?
Well, if you think about when we do our shifts,
Maybe it's always to the positive side. And then
so if you were adding and subtracting to the whole function, it moved it up and down. When you're adding and subtracting just the variable portion, it was always backwards. So minusing 2 from a function actually moved in the positive direction of the x-axis, and this is pretty similar to that thing there. Okay. I think though I can copy this and leave the original. Okay. So let's leave the original one there and just make our changes so we can go back and compare. Okay, so there's the same thing. I think that's the one that changed in this one, right? Just that minus 1. I don't think it's meant to be. I think it's meant to be separate from that. Okay, so there are the 2 of these. Let's change the color of the new one. Apparently, larva means color in this language.
Nedavno.
She's reading something, some new.
All right, so that dark blue one is the new curve, and we can see that's basically just been shifted. So when we subtracted 1 from the cosine of t, and if it had parentheses around t minus 1, then I would do that differently. So cosine of t minus 1, and it moved it back in the x direction. And I'm just going to tell you now, I am not going to expect the same level of replication of this that I expect of college algebra students. You don't have to know if you subtract from here, multiply by here, it changes things. I just want to show that those transformations do exist. If you needed to go through and generalize them, you could, but we're not going to worry about that. Okay. If we look at this from that other direction, from that more three-dimensional direction there, we still really have just the same curve, just it's been scooting over. It hasn't changed it too much there. If we look at the next one, so B compared to A, the change is now instead of a 1/2 t, we have a 2 times t. Let's change the color of that one.
Yeah, I thought it was last week.
Okay, so now there's that red curve. What change did this make?
Lengthened it.
Yeah, just like stretched it up. Does that make sense? If we look at this from the top down, it should look the same exact thing as the first one, right? Still just a circle there. I should zoom out so we can see more red. Okay, so we still just have that same circle, but now instead of, the z is increasing a lot quicker. Okay, instead of increasing by a rate of 1/2 times c, it's increasing by a rate of 2 times c. So we basically just took the same circle and just stretched this thing out further there, which hopefully makes sense. Got a couple more to look at. This isn't so bad in a different language. I kind of wish I knew what language it was. So c, we have cosine of negative t. And sine of negative t. So we flipped all the t's to negatives. Any guess what's going to happen here?
Upside down. Or backwards.
Yeah, upside down. Okay, it basically now flips everything in the other direction. So it's like taking that same curve and we're traveling backwards on that path there. So the curve is now going downwards instead of going upwards. Let's change color to 2. Okay, so we can see that it's just the other half of that, the bottom half of that. Oh, how many do we got left? 2 more left. What do you think is going to happen in D? What are the changes there? We have, well, we totally reordered things, right? Now my x component, instead of being cosine, my x component is 1/2 t.
Wider. Double.
Well, but now look what happened to my z component. So this is still 2 sine of t. My z changed to 2 cosine of t.
Maybe snap.
Mm-hmm. Oops. 2 times cosine. Okay, so now our curve is basically going in the other direction there. And let me change the color again. So let's say purple. Sounds good. Okay, so for this one, if I look at this one from down that x-axis, now there I have that circle. It's just basically been stretched in a direction there. So it's actually still the same shape we had before, just the orientation of it is different there, which hopefully makes sense too. All the components of this last one are the same, just in a different order. And so we just changed the orientation of what we were working with. And the last one, what changes there? How does E differ from the original one?
It's going to be 6 times.
Yeah, we got 6 in front of our trig functions. Now, what does this 2 represent right now in front of our trig functions? What does it represent in terms of this picture?
Like the radius is 2.
Exactly, the radius of the circle. So if I change it to 6, what should be the radius of the circle?
3.
No, radius is just r here, so it's going to stay 6. So essentially, we're going to have the same picture, but now my circle is going to have a radius of 6 instead of a radius of 2.
Right.
So my circle gets bigger. Okay, and there we go. But it still has that same stretched out spring shape, still goes up to the same point because the z component hasn't changed there. Okay.
Wow.
So point is, don't just think about them as equations. You can do that and you can go through the class and probably be okay, but it's going to be a lot more useful to you if you remember that these equations are representing things. Okay, I mean, unless you're a pure mathematician, you're not just going to do math for math's sake. You're going to do math because it relates to something else, and you're trying to model some process there. So the more you can understand how these functions relate to things like this, how they relate to graphs, and how you can modify them and change them, sure, it'll make it a little harder now, but it's going to be a lot more beneficial to future classes. Okay, so don't just think about them as equations. Really try to think about them as representing things. In this case, representing these paths that travel through space there. Okay. So if anyone figures out what language I'm in or how to fix it, feel free to share. But thank goodness this is just a math class, and cosine is still cosine. So like I said, I'm not going to be responsive. I'm not going to expect you guys to say, okay, if I have this -1 here, explain to me what changes makes to the graph. Okay, if you can tell it shifts it, that's great there. But what I really more care about is just being able to kind of reason through how these things relate and why that happens there. But you don't have to explain to me exactly what that -2 is going to be your graph. I don't think that's useful. Okay, so back to limits with these guys. We talked a little bit about limit, or actually we didn't talk about limits. We talked about domains. So talking about limits of vector valued functions. If you remember that a vector valued function is still a function, okay, it's just a function of a bunch of vectors here, all the things that we do with functions before, we're going to be able to draw pretty much parallels to now. And one of the first things you learn about in calculus with functions is going back and doing limits. So we're going to revisit limits. Each part of our vector value function, I heard that groan, each part of our vector value function is an individual function, basically. So when we are working with this x component, 3t is a function. When we are working with this y component, this is a function. They're each little functions in themselves there. There's really not going to be anything tricky about doing this. If you remember, the easiest way to evaluate a limit is to try to just plug it in, do direct substitution. Same thing's going to happen here. So for example 8, if we're finding the limit as t approaches 2 of that vector valued function, we're just going to take 2 and plug it into each component and see if it works. Now, if we run into problems like we get things are undefined or we can't evaluate it, that's where we have to go back and use different methods there. But I mean, it's pretty much just what we know with limits. We're just doing it 3 times instead of doing it once there. So nothing too crazy with this. Okay. So for example, in number 8 there, if we were to think about what this vector valued function does, it's basically traveling some path through space here. Goodness, talking. And I won't go through and graph it. It's a fairly, I don't want to say anything straightforward here because none of it is, but no trig functions, anything like that. It's fairly simple pieces that we're working with here. So it's just telling us some path we're traveling through space. Okay, if we went through and graphed it, we could. But really what we care about here is, okay, as t approaches 2, and if we think about this in terms of time, if you imagine there's like just some bug flying along this path here, after he's 2 seconds into his path, really what this question is asking is, where is he? What's his location? Where is the x value, the y value, and the z value at that point in time there? So like I said, if we just go back and use direct substitution, okay, that's the easiest way to do limits in Calc 1. It's the easiest way to do limits in Calc 3. Whether you want to do it as 3 separate pieces or you want to do it all at once, well, it doesn't matter. So we're going to have 3 times 2 in the I direction, plus 2 over 2 squared minus 1 in the j direction, plus 1 over 2 in the k. And as long as each of those is something you can evaluate, then we're done. So 3 times 2 is 6i. This gives me 2 over 2 squared minus 1, so 2 over 3j, plus 1/2 k. And that is it.
That's it?
That is it. So you're going for no reason. It was easy. Okay. But what this is telling us, remember, is just basically, well, where is it? Okay. As we get closer to this point, what happens here? Now, we will occasionally run into situations where, like, if I try to evaluate t approaches, say 1, which I won't go through and do right now. But what issue we're going to run into if t approaches 1 with this problem?
The second piece.
Yeah, that second piece is going to fail. Okay, we're not going to be able to go back and evaluate that. And so this basically leads into continuity, is what we're going to talk about with this. But if we do run into things like that, then we can go back and say, okay, we'll try all the things we did before. Can we factor to remove that? Is it removable, non-removable? Or we're just kind of stuck with it as a function undefined at that point. But we'll see some more examples to talk about that as we move throughout it. But for the most part, if limit exists, direct substitution, just figure it out. It's the easiest way to go through and do it there. Okay. Now this here, I was going to draw a picture myself, but I'm just going to sketch it here and then show you what we had in the book. So the idea is, remember that this vector valued function is just some path through space. Okay, I mean, we don't know what it is, but just some path through space is what this vector valued function is. When we are working with this, it is still vectors. So if we imagine this is our origin, okay, whether 2-dimensional or 3-dimensional, the idea is still the same here. Really what we're doing is we're saying, okay, if we've got this vector valued function, it's really just a whole bunch of vectors that are pointing to different spots here. And like we mentioned, we were graphing this yesterday, we don't really want to show those vectors, but just the endpoint that we get to. But behind the scenes, there's an infinite amount of little vectors here that are kind of drawing this path as we travel throughout it there. So what this has to do with this vector value function piece here then is, let's say one of these guys is the limit function that we're actually trying to get to. There's going to be some vectors. Okay, we're always working with vectors. So there's this actual point we're trying to get to. And what we're saying is, well, what happens if this here is r of t? Okay, at some point there along that path here, what we're really doing is looking at the difference between these two vectors there. I kind of drew my original curve a little too straight at that point. But we're saying, okay, as this t gets smaller and smaller and smaller, so closer and closer and closer to bring us to this L vector, we just want to make sure that this distance approaches 0. And that is a 0 vector. Okay, there would be nothing there. This is kind of similar to like epsilon delta proofs. We're not going to do an equivalent of that here. But if you remember what you're talking about epsilon delta proofs, you're saying, okay, as our as we get closer and closer and closer to the value we're plugging on the x-axis, that's the idea of delta. We want to know what does delta have to be to make this work in order to be able to be closer and closer and closer to that value on my y-axis there. The book does a better job of drawing this. So here's a better drawing of the same thing just from your book there. So if we have this path we're trying to travel on here, we have the limit that we're trying to approach there, and this is the origin. Okay, what we're looking at saying, okay, well, what's this difference? As that t value we're plugging into our r vector gets closer and closer to whatever the a is we're interested in this problem here, we should expect to see this distance get smaller and smaller and smaller. Which is kind of showing it. As that t gets closer and closer and closer to 0, or to a, what we're expecting to see there is that distance gets closer and closer and closer to L. Okay, so that's that t approaching A. A is going to end up hopefully right here for us. Let's go smaller and smaller. Yeah, I don't want to get too into this, but similar to the epsilon delta proofs in Calc 1. Okay, but we're not going to go through and prove it. What this leads to, though, is, like I said, continuity. We really want to have a way to define if a vector valued function is continuous or not. Okay, and that's what we have right here. So continuity of vector valued function. And actually, let's draw a parallel here. How do we define continuity in regular old x and y? How do we know if a function is continuous on a regular 2D graph?
No gaps.
No gaps, no jumps, okay? We kind of tell our classes before calculus, if you can draw the function with never lifting your pencil, it's a continuous function here. We know we have to use ideas of limits to give us a full definition later, but same idea here. So a vector valued function of 3 dimensions is continuous, basically the same thing. If you can draw it whenever lifting your pencil, it's probably going to be continuous there. But the more mathematical definition is right here. So R is continuous at some point, and there's that point we're continuous at. When not only does the limit exist, but we have this property right here. So the limit as we approach that point and the value of the vector function at that point are the same thing. Okay, which is basically just saying you don't have any holes, you don't have any breaks, no jumps in your graph or anything like that there. Okay? Since finding the limit is super easy, just direct substitution, and since the right half of this equation is just direct substitution, this really isn't going to be too difficult to show for most cases here. Okay, and it's going to be pretty obvious if it's not continuous. If we have problems like this guy right here, he's going to have problems with continuity because of the rational function there. But let's go in the order I have them. So we got this function here. R equals t in the I direction, a in the j direction, and a squared plus t squared. And I am going to go through and graph this. The only ambitious.
Do we always have to graph?
Nope, I just like to.
Okay.
I draw pictures in all my classes. Ask my stats class. I draw more pictures than they probably care to see.
Oh, press the 7 button. Go to all the way down
Like here.
and press the 7 button again.
This one.
Yeah.
And first one, that's language.
Oh my goodness, that's wonderful.
Use the other way.
Let's go to actually good old US English. Oh, thank you so much. That's so much nicer. All right. I don't know how I changed that in the first place, but thank you very much, Russell. All right, so let's go ahead and graph this. Example 9, we have t a squared minus t squared. And we want to add some sliders. Okay. Did it do it? Oh, not for t. Well, that didn't work. It created a slider for the wrong thing. Okay, I won't be able to graph this one. I don't know GeoGebra quick enough to fix that. So I guess we can put numbers in. All right, let's just make up a number for A. What's your favorite number, Brett?
13.
Okay, so let's say A equals 13 for this problem. Okay, woo, let's pick a small one. 13 is really big.
Okay, 5.
I'll just zoom out a lot. How about that? Okay, if I keep zooming out, pick 13 for A was a really big number, so my problem is huge there. But there is the function that we're working with. If we pick a smaller number for that instead of, we would have a much smaller problem. But there is the path that we're talking about here for this one. Okay, do you need to see this for this problem? No. But just to try to hopefully start getting us more familiar with vector valued functions, I will definitely try to graph them there. So if we were to let A equal 13, here is the graph that we get for example 9 there. But all this problem wants to know is about the continuity. So whether we look at the graph or think about the function, is there anything here that sends up a red flag and says something's not continuous? Like if you start drawing this function, are you going to have to like lift your pencil at any point? No, so it kind of follows a good old idea of what it means to be continuous. The graph looks nice and smooth. If we think about each individual component, do any one of these components have restrictions? So if we just remember, A is just some constant, whatever constant we want it to be. If we think about each part of this, they're all okay. So for the X component here, okay, the domain for this is just all real numbers. Okay, there is no restriction on here. T can just be whatever you want it to be. Okay, for the Y component, it's just some constant. So again, same idea. Doesn't matter what that constant is. It gives no restrictions on T. T can be anything. And then similarly for the Z component also. So for all these pieces, if we were talking about the domain of this graph, and remember, domain and continuity have a lot to do with each other. So if we think about the domain, that helps us with continuity. But there's nothing here that really is going to cause a problem with that. So try to keep those things in mind here. The domain of this graph is all real numbers. I know it didn't ask that, but it's still useful to be aware of. Let's do it this way. I wanted to write it this way. Do we know what that notation means?
Yes.
No. Okay, so T is the variable we're working with. That little weird E thing means belongs to or is a member of, and that R with 2 lines is same for real numbers. So that says the same thing as this above it. It's just a much shorter way of writing it. Okay, but T can be anything, any real number. Okay, from negative infinity to infinity. I just want to remember that it's T we're talking about, not an individual piece here. But what this question actually asks is the continuity at this point T equals 0. So the easiest way to go through and do this has nothing to do with what I've shown you guys just so far. The definition we just saw on the last page says, okay, the limit as T approaches 0 needs to equal the vector value function at 0. So if we go back and actually check what this is asking for, we need to do this. We need to show that the limit as T approaches 0 of this vector valued function is equal to the vector valued function at 0. Okay. This work is going to seem really silly to do at this point because we're going to do the same process on both sides. The way we said we go back and find limits with direct substitution. So if I think about answering this left-hand side, we're going to have 0 in the I direction, plus A in the J direction, plus A squared minus 0 squared K. And if we reduce that down, that's nothing for I. A times J plus A squared times K. Okay, so just simplifying that down there. And that's the limit. As we approach 0, the limit is that vector right there. But when we go back and evaluate this vector value function, we're going to do the same exact thing, so the work's not going to look any different. If I go back and let T equal 0, it's, like I said, the same exact thing we just did. So yeah, obviously, it's not a problem. Okay, but what this shows is that the vector value function is continuous when T equals 0. Okay, so that's kind of the actual answer that this thing was asking for here. Most of the things we're going to work with will be continuous, or it'll be obvious that it's not continuous there. And we'll look at the graph the next one where we have a problem with that. But that's what we're going through and showing there. Like I said, I really encourage you guys not just to think that this is a math problem, but like, what does this mean? How does this relate to other things? And hopefully just makes it easier to kind of keep growing with it there. But anyway, that's the definition. It is continuous at T equals 0. That's the answer to the question there. Okay. All right, so same question for number 10. We have different vector valued function. This one doesn't have any of that X or that Z component on it. So if I go back and graph this one, I'm going to use Desmos just since it's two-dimensional. It just looks a little nicer and easier to work with there, but you can use GeoGebra for it also. T1 over T. All right, so here is that vector valued function. Let's make the T a little bigger. Okay, and this hopefully isn't too surprising. I mean, if we consider this function here, it should kind of make sense why it looks like this with our knowledge of parametric equations. But the question is asking us at T equals 0, is this thing continuous? Does it look like it based on this graph? At T equals 0? Yeah.
No.
No, think about asymptotes. If the function has an asymptote, I mean, let's back up a minute. The whole function, sure, it's continuous. Okay, I can draw this thing with one line, that's fine. But only on a domain it's defined for. Is this thing defined when T equals 0? No, we can't do that. So it's not continuous at T equals 0 there. Okay, and again, just looking at the graph, sometimes it's enough to kind of tell you what the answer should be for these. But if we go back and do the same thing like we did up above there, what we want to show to see if it's continuous at t equals 0 is we want to show that the limit, let's write this the right way. We want to show the limit as t approaches 0 of the vector valued function is equal to the vector valued function at 0. If we can show that, then yes, it's continuous at that point. But we know we're not going to be able to do this. So if we go back and try, just to compare the limit, 0 in the I direction plus 1 over 0 j, and then we run into problems. And the same thing's going to happen when we go back and try to actually evaluate this. Okay. Is there anything we can do to remove that discontinuity? Can we somehow rewrite that component that we can evaluate this?
Could you make t to the -1?
If we made t -1, we wouldn't have any problems, right? If we change something like that, then we would be able to go back and evaluate this. But we need to try to address the point of interest, this guy right here. Okay, so let me give you a similar type of problem that you could have done back in Calc 1. If we were doing something like this in Calc 1, give me a minute to make sure this works. Let's put the same variables in place is helpful too. Okay, if we had this problem and we were trying to solve this in Calc 1, we went back and did direct substitution, where we get 0 over 0, so we can't finish it. What would we do in this case? Would we say it's not continuous and move on? Or what do we do? We factor it. Good. I heard someone say we factor it. So I can take this, and this is the same thing as limit. T approaches 2, t minus 2 over t plus 2, t minus 2. Those guys cancel out, and yay, now I can go back and I can evaluate this limit, right? So that's kind of what I'm asking to do here, is can we do something like that to this problem that we're working with now in 3 dimensions? Is there a way I can fix this discontinuity, that I can rewrite the problem to remove it? So if I have 1 over t, can I factor that?
No.
No, I really can't do anything with that. It's very simple. There's not really much to it. This is a non-removable discontinuity. Okay, asymptotes always are going to be. You can't do anything about those. So there's really nothing else we can do on this problem. We went through to try to show if it's continuous. It wasn't. We can't do anything to rewrite this component to fix that problem. So the final answer for this would just be that this vector valued function, so r of t, is not continuous when t equals 0, or at t equals 0. Okay, there's nothing we can do about that. It is just not continuous at this point. How about example 11? When I look at the graph, are there going to be problems on this one?
Yes.
Yeah, this is just in general. When is it continuous there? Again, go back to domain. If we think about the x component, when x equals t, okay, if that's our very first component, there's no restrictions on that, so you can get anything. Okay, how about for that middle component, that y piece, that j component? Is that going to have restrictions?
Yes.
Yeah, okay, we can't get a negative under the radicand, so we're going to have some kind of function there. So let's do this problem as consider the domain. Okay, if we consider the domain of this, for our x component, like we just said, that's just all real numbers. No problems there. For our y component, that's where we're going to have issues. Okay, so if we go through and think about this one here, what are we working with? Anything from 1 and bigger, right? So from 1 to infinity, the domain of this one. How about for the z component? Any restrictions there?
No.
No, that's all real numbers too. So this is really what we just have to consider. We can say, okay, as long as I'm plugging in a number that satisfies this part, the whole function is going to be continuous there. Oops, pen's a little funky, sorry. So we could say r of t is continuous. Goodness, sorry, my pen's battery is on the fritz. Let's say this 4, that makes more sense than when. Okay, so as long as t belongs to this thing here, so for when t is in the domain, for when t is in the interval from 1 to infinity, this thing's going to be continuous. And just because I talked about graphing these, let's go ahead and put this one over here too.
Oh boy.
All right, zoom back out. Okay, so there is that function we're working with here. And I don't know how to change the restrictions quick enough there, but we've got this little part of a parabola, which kind of makes anything else squared functions. So there we go. It would continue up if I fix my graph a little bit, but the reason it starts here is because we know we can't have t values be less than 1. So our graph has a starting point there. Okay. All right. Okay. Questions? Okay, we've got some time. Let's start the differentiation piece. So next section. When we first learned about derivatives, what did we say? What is a derivative? I'm going to say first derivative. What does the first derivative tell you?
The change the slope.
Yeah, the slope, instantaneous slope. So if we want to find the slope of something for lines, it's very easy. It's just the slope from mx plus b. But we know that anything can have an instantaneous slope, it just kind of changes there. So what is derivative? Specifically, first derivative, we know tells us slope. Or if you want to call it the instantaneous rate of change, go for it. And then we know that second derivative tells us something different. Third, fourth, there's an infinite amount of derivatives, but usually we focus on first and second derivatives. We've had work out there. Okay, third derivative sometimes. Same thing with this. Okay, we're still talking about that rate of change or that slope. Now be careful thinking about it as slopes. Like we talk about with vectors. If we have 3 dimensions, it's not just slope anymore. We have to count for what direction kind of that slope is headed in there. So that instantaneous rate of change is probably a better way to think about it, but it still means the same exact thing. R is a vector valued function, so we can find the derivative of this vector valued function. If we think about the path that this thing is traveling on, the question then is, okay, after like say 1 second has passed, how quickly is this thing moving and in what direction is it moving there? So we can go back and find speed and we can find velocity along this path here. The definition for it is right here. We're not going to really worry about working through and doing the limit definition of this too much. Because we've got much more efficient ways of going through and doing it. But there is a limit definition for going through and find this. Does that look familiar?
Yes.
Yeah. Back to Calc 1, it's essentially the same thing. Okay, we have a vector valued function, so for a regular function, we use t instead of x, but it's saying the same exact thing here. If we have our vector valued function at a specific point, and we make some small change to that point, as that small change gets smaller and smaller and smaller, or we're getting closer to that really instantaneous piece there, we're just really finding the slope or the rate of change between these 2 points here. So this is the same thing we talk about in Calc 1, we just have it now in vector valued functions instead of good old-fashioned functions. Okay? I go through and talk a little bit about closed intervals, one-side limits, and all that good stuff there. But keep in mind, we are working with a vector valued function. So if we take the derivative of a vector valued function, we still get a vector. So adding vectors, subtracting vectors, multiplying vectors, all that stuff still applies. So we can add and subtract vectors, just like we did in the last chapter. We can find dot products or cross products, just like we did in the last chapter. We'll also talk about working with unit vectors. Okay, basically everything we talked about in the last chapter of vectors applies because they're still just vectors. Okay, so they have different application because they're kind of trying to follow this path through space, but it is still a vector and still do all the good old-fashioned stuff to it. Okay. There also is really nothing tricky about finding derivatives. The only thing that's going to make derivative tricky is if the component itself is tricky to work with a derivative of. But the way we find derivatives of vector valued functions is we just find the derivative of each component. That's all there is to it. It is not difficult. The only part about this that'll be difficult is, like I said, when the components actually are difficult functions to work with. But if you've got some vector valued function R of t, so there's f, g, and h right now, our x, y, and z components to this, as long as we can find the derivative of that x component f, or that y, or that z, we just find the derivative. So using product rule, quotient rule, all those rules still apply, and that's what makes this difficult. Okay, the Calc 3 piece just says do it 3 times, so just do it once there. We won't talk about it because it's hard to think about graphing it, but if you were working with like a 4 or 5 or 6 or whatever dimensions, so you can keep tacking on components to this, the process is still the same. Okay, so whether you have 3 variables or 100 variables, we still do the same thing. So yay, we finally get to some calculus. Here we go. Example 1. Find the derivative of the vector value function and sketch the plane curve represented by the vector value function and the graphs at those points there. Okay? So there's my vector value function. Let's go through and find the derivative. And notice we'll use basically the same notation, r prime of t. So what is the derivative of t? Just 1. We're going to have 1 in the I direction. Okay? We don't have to find a product. Remember, all that I is telling us to do is this is the direction that we're traveling. The coefficient or the component part of that is all we're finding the derivative of. So if we follow that to the next one, what is the derivative of t squared plus 3?
2t.
And then plus 0 or just 2t, and that's it. That's the derivative. So again, the I and the j just kind of stay there. They're telling us the direction this change is happening in. We're just going to take that component or that coefficient, you can think of it as, and find the derivative of that. So there we go. That is it for the derivative of the vector value function. Like I said, it is not meant to be tricky. It is just find the derivative there. So the other part of this, going through and graphing it. I'm going to graph it in Desmos because I can. It goes a little faster and looks a little nicer, but you can go ahead and sketch it in your notes here too. So our original function we were working with is t squared plus 3, not equal to 3, plus 3. And let's get more values of t here. Okay, so that's what we're working with. We have just basically a parabola is what this shape is. Okay, it's been shifted up 3 units, but it's just a standard parabola that's been shifted up 3 units. If you wanted to put the direction with this, it is going from left to right there, very standard shaped parabola. So that's that curvature equation. If we go back, actually I do want this in the notes, I want to sketch on this. So 3 passing through these points. So kind of like this. Okay. All right, let's go back and add a couple things to this. So let's go back and find the value of the vector value function at 1 and the value of the derivative at 1. So that's just substitution. Into the vector value function, we're going to have 1 in the I direction plus 1 squared plus 3 in the j direction. Now I'm going to go to component form. It's much less stuff to write. So it's vector 1, 4. If I plug a 1 into my derivative, it's going to give me 1 in the I direction, plus 2 times 1 in the j. So vector 1, 2. Okay, so what does this stuff mean here? Well, like we said, we know that when we're working with these vector value functions, we usually just care about the endpoints. But remember, we've talked about what this one means already. This is like the stuff we had in the first section there. Sorry. All that's doing is saying, okay, well, how did I get to that point? From the origin, I followed that vector. Okay, which makes sense. It's a point on my curve. Ta-da. We don't usually draw those vectors in there, but there's an infinite amount of these vectors in here drawing this parabola out. Okay, well, the derivative, that's really what I want to mention here. What does the derivative mean? We said derivatives talk about instantaneous rate of change here. And in 3 dimensions, we can't just report a slope. We have to do more than that. So we're kind of doing a similar thing in 2 dimensions here. But if we think about going back and graphing this, typically we'll graph these from the origin, right? In component form means it starts at the origin. We have this. Well, that really doesn't look like it's telling me much for my actual function here. So it's not uncommon to say, okay, here's the point that we are plugging this in for. And that's why I went back and graphed that vector 1, 4. If we plug t equals 1 to the original function, here's a position it takes me to. From that position, if we go back and graph that slope, okay, and my parabola isn't drawn very well to make this look right, but if we go back and plot that slope from that position, the slope should try to mimic the shape of my curve. And let me draw my parabola a little better to hopefully catch that. That's a little better. Still not a great parabola. But yes, 1, 4, and 2, 1 are both in component form, which means typically they start at the origin here. But try to think about that derivative saying, okay, after I go to this point, I'm on this curve. This vector 1, 2 tells me, okay, from there, what's that rate of change? Okay, we're going 1 in the x direction, 2 in the y direction, which if you think about slope, it's just a slope at this point. But that's really what we're doing when we're working these vector valued functions or derivatives. We're saying, okay, yes, it tells me the rate of change, but imagine it is from that location. And that just might make it make a little more sense when you visually think about this here. Okay. The actual process of finding the derivative is pretty simple. But if we can try to remember what we're working with, it's saying, okay, from this point, here's what we're doing. We're going off in this direction at this rate. If our vector was longer, it means we're traveling faster. If our vector is short, it means we're traveling less. We'll eventually talk about speed with this stuff too. That doesn't happen for a little bit yet. Okay. Let's get into this one. I guess questions so far? Maybe I should ask questions. Sorry, my graph's not fabulous, but that kind of makes sense why we're moving that vector there. Okay, let's do a couple of these, and then we'll finish this example up next time. So for the vector value function below, find each of the requested. So now we do have a three-dimensional piece here. This is not quite a circle since we have sine of t minus cosine of t. We're not quite working with a circle here on this one, but we're close out of time, so I won't graph it until next time here. We'll just go through and do the math. So we want to find the derivative of the vector value function. So what is the derivative of the sine?
Cosine.
And then we just tack on the I direction. Remember, we're not using product rule. We're just saying derivative of that coefficient piece is this. What is the derivative of the cosine?
Negative sine.
So we can write that definitely more efficiently as plus sine. I'll go back and do that in a minute. And then what is the derivative of 3t?
3.
Okay, so if you want to write it in linear combination form, go for it. If you'd rather write it in component form, that's okay too. But that's it. I mean, really, finding the derivative is only difficult when the functions you're working with are difficult. Okay, so don't forget all the things you know about finding derivatives. Integral is going to have a very similar thing here. But there you go. That's all this is asking for. I didn't specifically say this in the last page, but how do you think you find the second derivative?
You do the.
Just do it again, exactly. You take the first derivative and find the derivative of that. I mean, really, this some stuff in Calc 3 is like stupid simple. So what's the derivative of the cosine? It's negative sine of t. The derivative of the sine is cosine of t. And what's the derivative of 3?
0.
So we have no k component. We can just leave it off there if we want. Okay. If we write this in component form, we have negative sine t, cosine t, and then just make sure you do include the 0 in component form. Okay. We want to show all 3 pieces. But that's it. Okay. Again, some of this stuff really isn't all that difficult. The understanding the application of it, yeah, that part can get difficult. But the math behind some of this is pretty straightforward. Okay. But we'll stop there. We'll review dot product and cross product next time. Talk more about the use behind this. The homework for this is posted. If you want to get started on it, go ahead. But if you haven't taken your test yet, then just please focus. Okay. So, any questions?
My WebAssign is good now.
Okay, it's good now. Excellent. I'm glad that got figured out. Did you have to do anything, or did they fix it for you?
Huh?
Did you have to do anything, or did they fix it?
No, I got an email that my unlimited access had timed out, and then I went on today and looked at it, and it didn't say anything. It just let me type in answers. So.
Okie dokie. We'll just go with it then. Excellent. Glad it's working. All right, everyone. Enjoy your weekend.
All right,
Okay,
see ya.
you too.